Let us begin slowly and with a little patience, because the ideas we are about to discuss are simple in spirit, even if they sometimes feel technical at first. In linear algebra, we often work with objects we call vectors. A vector is something that can be added to another vector, and it can be scaled, meaning we can stretch it, shrink it, or reverse its direction by multiplying by a real number. That is the basic structure. And much of linear algebra is about learning how to describe that structure in a way that is both flexible and precise. A recurring theme will be this: there is the underlying abstract object, the vector itself, and then there is the description we choose for it. The vector is what it is. But the coordinates we use, the basis we choose, and the matrix we write down, those are choices. Useful choices, powerful choices, but still choices. So we will move gently through 6 connected ideas: bases, dimension, coordinates and changing bases, linear maps, kernel and image, and the rank nullity principle. Each idea will echo the previous ones. And it is worth repeating from the start, linear algebra is, in a sense, the art of choosing a language for structure, and then using that language carefully. Let us pause and reflect on that. We are not merely computing. We are choosing a viewpoint. We are choosing a coordinate system. We are choosing a way to speak about vectors and maps. And when we choose well, the structure becomes calm and transparent. Now let us talk about bases. A basis is often introduced as a technical definition, but I want to start with a phrase that captures the feeling. A basis is enough pieces to build everything with no redundancy. Enough pieces to build everything means that every vector in the space can be assembled from those basis vectors using addition and scaling. You take the basis vectors, you scale them, you add them up, and you can reach any vector you want. And with no redundancy means that none of the basis vectors is unnecessary. You cannot throw one away and still build everything. Also, no basis vector can be built from the others. Each one contributes something genuinely new. So again, a basis is enough pieces to build everything with no redundancy. It is worth repeating because that single sentence carries 2 crucial ideas: completeness and independence. Completeness says you can build everything. Independence says you are not repeating yourself. Now, the soothing and important fact is that there are many bases, usually infinitely many. And that is not a problem. It is freedom. The space itself is fixed, but the basis is a choice. Choosing a basis is like choosing a coordinate system. It is like deciding which directions you will treat as your basic directions. And because many choices work, choosing a basis becomes part of modeling. It becomes part of deciding what you want to emphasize. If you are thinking about physical space, you might choose the familiar directions: left, right, forward, back, up, down. But in other contexts, you might choose directions that match the problem. You might choose directions aligned with a surface, or aligned with constraints, or aligned with measured data. So let us make that explicit: choosing a basis is modeling. A basis is not a property of the vector space in the same way dimension is. A basis is a tool we pick to describe the space. Now here is the deep payoff of having a basis, and it is worth repeating because it is central. If you have a basis, then every vector has unique coordinates. Meaning, once you fix your basis, there is exactly one way to describe any given vector as a combination of those basis vectors. Not many ways, not several competing descriptions, but exactly one. So, basis implies unique coordinates. And that is not just convenient. It is the reason coordinates are meaningful. If descriptions were not unique, coordinates would be ambiguous and unreliable. The fact that a basis has no redundancy is precisely what makes coordinates unique. Let us pause and reflect. A basis is a set of building blocks that can construct every vector, and none is unnecessary. Because none is unnecessary, you cannot represent the same vector in 2 different ways using those building blocks. And therefore, once the basis is fixed, every vector has one and only one coordinate description. It is worth repeating, basis implies unique coordinates. And as we move forward, we will keep returning to this. We will use bases to turn abstract vectors into coordinate lists, and we will use linear maps to turn abstract transformations into matrices. But the abstract objects come first. The coordinates come from our choices. Now let us move gently from basis to dimension. Dimension is the number of degrees of freedom in a vector space. It is the number of independent directions available. If you are in a space that feels like a plane, you have 2 independent directions. If you are in a space that feels like ordinary three-dimensional space, you have three independent directions. But linear algebra is broader than physical space. So dimension is defined in a way that does not rely on geometric pictures, even though those pictures help. Here is the guiding idea: the dimension of a vector space is the number of vectors in any basis. And because a basis is enough pieces to build everything with no redundancy, the number of basis vectors is telling you how many independent directions you truly have. Now, students often worry, if there are many bases, could different bases have different numbers of vectors? The reassuring answer is no. That is one of the most stable facts in linear algebra. It is worth repeating: dimension does not depend on the basis. You can choose many different bases, but they will all have the same number of vectors. That common number is the dimension of the space. So bases vary. Dimension does not. Choosing a basis is modeling, but the dimension is an intrinsic feature of the space. Let us pause and say that again in slightly different words. A basis is a coordinate system you choose. Different coordinate systems exist. But the number of coordinates you need, once you choose any system that truly captures the space without redundancy, is fixed. That fixed number is dimension. Now, another quiet intuition: constraints reduce dimension. If you start with a large space and then impose conditions, you often restrict the freedom. You remove some directions, and that usually lowers dimension. For example, imagine a space of objects where you originally had 3 degrees of freedom, but then you impose one independent constraint. The resulting set often behaves like something with 2 degrees of freedom. In linear algebra, when we talk about subspaces, we are often talking about spaces defined by linear constraints, and each independent constraint tends to reduce the number of independent directions you can move. So it is worth repeating: constraints reduce dimension. And we will see later that the kernel of a linear map is like a set of vectors that satisfy a certain condition, namely that they are sent to 0. That is a constraint. And the image of a linear map is like the set of outputs that are possible. That too is a kind of restriction. These ideas will connect back to dimension in a very calm and balanced way. But for now, we keep the core message: dimension is the number of independent directions. Dimension is the number of vectors in a basis. Dimension is stable. It does not depend on which basis you choose. And constraints reduce dimension. Now that we have bases and dimension, we can speak calmly about coordinates. Coordinates are not the vector. Coordinates are a description of the vector relative to a chosen basis. This is one of those statements that is worth repeating often, because confusion here can make later topics feel harder than they are. A vector is an abstract object in the space. Coordinates are the numbers you write down after you choose a basis. So the coordinates depend on the basis, not on the vector itself. The vector stays the same, but the coordinate description changes when you change your basis. Let us pause and reflect. If 2 people choose different languages to describe the same idea, the idea does not change, but the words do. Similarly, if 2 mathematicians choose different bases, the vector does not change, but its coordinate list does. That leads naturally to the idea of change of basis. Change of basis is translating descriptions between languages. You have one basis, and therefore one coordinate description. You have another basis, and therefore another coordinate description. And change of basis is the systematic method for converting one description into the other without changing the underlying vector. It is like saying, here is a sentence in one language, and here is how to express the same meaning in another language. The meaning is the vector. The language is the basis. The translated sentence is the new coordinate list. Now, change of basis can feel like bookkeeping, and in a sense, it is. But it is meaningful bookkeeping. It is bookkeeping that preserves structure. And it is worth emphasizing, we are not doing arbitrary conversions. We are translating in a way that respects addition and scaling, because those are the core operations of the vector space. So change of basis is not merely a trick. It is a structured translation. Let us say again, slowly, coordinates depend on your chosen basis, not on the vector itself. Change of basis is translating coordinate descriptions from one basis to another. And careful bookkeeping matters, because if you mix the languages, you will confuse descriptions that were never meant to be combined. Often, the reason students stumble is not because the concept is deep, but because they unintentionally switch bases mid-problem without noticing. They add coordinates expressed in one basis to coordinates expressed in another basis, which is like adding words from different languages without translating. So it is worth repeating, always know which basis your coordinates belong to. And in later topics, when we talk about matrices, we will see that the matrix you write down for a linear map depends on your choice of basis in the input space and your choice of basis in the output space. The map is the true object. The matrix is the representation in chosen coordinates. So again, the steady theme: objects are abstract, descriptions depend on choices. Now we move to linear maps. A linear map is a function between vector spaces that respects the vector space structure. And that structure, again, is addition and scaling. So let us define linearity in words slowly. A function is linear if it preserves addition and it preserves scaling. Preserving addition means, if you add two vectors and then apply the function, you get the same result as if you apply the function to each vector first and then add the output. Preserving scaling means, if you scale a vector by a number and then apply the function, you get the same result as if you apply the function first and then scale the outputs by the same number. These two preservation properties are the heart of linearity. And it is worth repeating, linear maps respect structure. They do not twist the rules of addition. They do not twist the rules of scaling. They keep the algebra calm. Now, a gentle geometric intuition: even if we do not rely on pictures, linear maps preserve straightness, mixing, and the origin. Preserving the origin means that the zero vector is sent to the zero vector. This is a quiet consequence of preserving scaling. If scaling by zero collapses everything to the zero vector, then applying the map must respect that collapse. Preserving straightness means that if you move along a straight line through the origin by scaling a vector, the map will send that to another straight line through the origin. It does not bend it into a curve. Preserving mixing means that if you form a combination of vectors by scaling and adding, the map distributes through that combination in a predictable way. So we can repeat this common phrase: linear maps preserve straightness, mixing, and the origin. Now let us emphasize another major viewpoint: linear maps are the true actors. Matrices are representations. A linear map exists even before you choose any basis. It is an abstract transformation between abstract space. A matrix appears only after you choose bases, because the matrix is how the map looks in coordinates. So again, linear map first, matrix second. The map is the underlying function that respects addition and scaling. The matrix is a table of numbers that depends on your chosen coordinate systems. And this matters because changing basis changes the matrix, even though the linear map stays the same. Let us pause and reflect. A linear map is a structure-respecting function. It is a transformation that behaves well with addition and scaling. Matrices are simply what we write down when we decide to speak in coordinates. Different bases produce different coordinate descriptions, and so they produce different matrices for the same underlying map. That is not a contradiction. That is the same idea we had with vectors. The vector stays the same, the coordinates change. Here the map stays the same, the matrix changes. So it is worth repeating, linear maps are the true actors, and matrices are representations. And again, linear maps preserve straightness, mixing, and origin. Now we come to two central diagnostic tools: kernel and image. When you have a linear map, you want to understand what it does in a qualitative way, not just in terms of particular inputs, but in terms of its overall behavior. Kernel and image capture that behavior. Let us start with the kernel. The kernel of a linear map is the set of all vectors that get sent to the zero vector. In plain words, it is everything that collapses completely under the map. If you input a vector from the kernel, the output is 0. The map cannot distinguish that vector from the zero vector, because both produce the same output. So the kernel measures lost information. It tells you which directions are erased. It is worth repeating, kernel means what gets sent to 0. And the intuition, kernel is lost information. Now let us talk about the image. The image of a linear map is a set of all outputs you can actually reach by applying the map to some input. It is the range of the transformation, but in linear algebra, we often use the word image to emphasize that we are looking at the set produced by mapping the whole input space. So the image measures achievable outputs. It tells you what the map can hit, what it can produce. It is worth repeating, image means what you can reach. And the intuition, image, is the set of achievable outputs. Now, it is helpful to hold both intuitions at once. Kernel is what collapses to zero, so it measures loss. Image is what can be produced, so it measures reach. Loss in reach. What disappears and what remains possible. Let us pause and reflect on a common mental picture described in words. Imagine you have a space of inputs. The linear map takes each input and produces an output. Some different inputs might land on the same output. In particular, all kernel vectors land on the zero output. If the kernel is large, many different inputs become indistinguishable after mapping, at least as far as outputs are concerned. At the same time, not every output in the target space may be achievable. The image might be smaller than the whole output space. If the image is small, the map cannot reach many possible outputs. So a kernel tells you about collapse, and image tells you about limitation. It is worth repeating, kernel and image are the central diagnostic tools. They are the first things to ask about when you want to understand a linear map. What does it kill, and what can it produce? And because these sets are themselves subspaces, we can talk about their dimensions. The dimension of the kernel is called the nullity. The dimension of the image is called the rank. We will not rush into naming, but we will hold on to the dimensions because they will lead to a common balancing law. Now we arrive at a principle that often feels, at first, like a formula to memorize. But I want you to hear it as a balancing law, almost like a conservation principle. Rank nullity is the idea that the total number of independent directions in the input space can be accounted for by splitting them into two groups. One group consists of directions that are lost, meaning they lie in the kernel. The other group consists of directions that are preserved in the sense that they produce distinct movement in the output, meaning they contribute to the image. In words, lost directions plus kept directions equals total directions, where lost directions means the dimension of the kernel, and kept directions means the dimension of the image, and total directions means the dimension of the input space. So rank nullity is a balancing law, lost directions plus kept directions equals total. Let us pause and reflect on why this should feel inevitable. Suppose you choose a basis for the input space, so you have enough pieces to build everything with no redundancy. Now, some of those basis directions might get sent to zero, or might combine in such a way that they do not create new output directions. The kernel captures exactly the directions that truly disappear, and the image captures the directions that remain visible in the output. Balancing law says you cannot lose directions without accounting for it. If the map loses many degrees of freedom, then the output it can produce must have fewer degrees of freedom. And if the map produces many independent output directions, then it must have lost fewer directions. It is a trade-off, but not a vague trade-off. It is an exact balance. So again, lost directions plus kept directions equals total directions. Now let us make the intuition more concrete with gentle examples described in words. First example. Consider a map from a three-dimensional input space into a two-dimensional output space, like projecting three-dimensional space onto a plane. In such a projection, there is typically one direction that gets collapsed, namely the direction perpendicular to the plane. Anything along that perpendicular direction goes to zero movement in the plane. That direction belongs to the kernel. The image is the plane itself, which has 2 degrees of freedom. So you have one lost direction and 2 kept directions, totaling 3. Second example, consider a map that takes a plane and squashes it onto a line through the origin. Then one direction in the plane is lost, and the image has 1 degree of freedom. Lost directions plus kept directions equals 2, matching the dimension of the plane. Third example, consider a map that is injective, meaning it loses no non-zero vectors. In that case, the kernel contains only the zero vector, so the lost directions are 0. Then the balancing law says the kept directions equal the total directions. In other words, the image has the same dimension as the input space. The map does not collapse any dimension. Fourth example, consider a map that is the zero map, meaning everything goes to the zero vector. Then the kernel is the entire input space, so all directions are lost. The image is just the zero vector, which has no degrees of freedom. Lost directions plus kept directions still equals total. It is worth repeating these extremes because they make the balance feel natural. If you lose everything, you can produce almost nothing. If you lose nothing, you can preserve the full dimensional complexity. And in between, there is a precise counting. Let us pause and reflect again. Rank nullity is not primarily about computation. It is about understanding. It tells you that every linear map partitions the input space into what is invisible to the output and what is visible through the output. The invisible part is the kernel. The visible part is what contributes to the image. And the dimensions add up exactly. So again, slowly, kernel is lost information. Image is achievable outputs. Lost directions plus kept directions equals total directions. And it is worth repeating that this law is stable. It does not depend on the basis you choose. You may represent the map in different coordinate systems, you may write different matrices, but the dimension of the kernel and the dimension of the image are intrinsic to the map itself. So the balancing law is about the map, not about the matrix representation. That connects back to our earlier theme, linear maps are the true actors. Matrices are representations. Rank nullity speaks about the actor, not the costume. Now, as you become comfortable, you may use the matrix representation to compute these dimensions, but even then, the conceptual meaning should come first. Because if you know what kernel and image mean, the computations feel like ways of revealing structure, not like rituals. Let us end by gathering everything together, calmly, and repeating what matters most. We began with bases. A basis is enough pieces to build everything, with no redundancy. It is worth repeating. Enough pieces to build everything, with no redundancy. Because of that, once a basis is chosen, every vector has unique coordinates. Basis implies unique coordinates. We then move to dimension. Dimension is the number of degrees of freedom, the number of independent directions. It is the number of vectors in any basis and it is stable. It does not depend on which basis you choose. Constraints reduce dimension because constraints remove degrees of freedom. Then we spoke about coordinates and change of basis. Coordinates depend on the basis, not on the vector itself. Changing basis is translating descriptions between languages. The underlying vector stays the same, but the coordinate description changes, and careful bookkeeping matters so that we do not mix languages without translating. Then we spoke about linear maps. A linear map is a function that preserves addition and preserves scaling. It respects structure. It preserves straightness, mixing, and the origin. And it is worth repeating, linear maps are the true vectors, and matrices are representations that depend on chosen basis. Then we introduce kernel and image. Kernel is what gets sent to zero. Kernel is lost information. Image is what you can reach. Image is achievable outputs. These two subspaces are the central diagnostic tools for understanding what a linear map collapses and what it can produce. Finally, we arrived at rank nullity, the balancing law. Lost directions plus kept directions equals total directions. The dimension of the kernel, which measures lost directions, plus the dimension of the image, which measures kept directions, adds up to the dimension of the input space. And this feels inevitable when you remember that a linear map cannot destroy degrees of freedom without reducing the complexity of what it can output, and it cannot produce many independent outputs without preserving many independent inputs. So we end where we began. Linear algebra is about structure, and about choices of description that respect that structure. And as you rest with these ideas, you can let them settle gently. Vectors are abstract, bases are chosen, coordinates are descriptions, maps are the true transformations, matrices are their coordinate costumes, and kernel and image tell you what is lost and what is reachable, while rank nullity calmly balances the account. Let us pause once more, and let that balance feel steady.